Let's finish up our checkpoints for our practice problems. Number 8. Amy is standing on the floor and pulling on a rope around a pulley and making a mass capital M rise at a given constant acceleration. Well, suppose I said to you, I wanted to know what the normal force was of the floor holding Amy up. She's not moving, she's just pulling down. Well, the problem with that is I could do my second law. I know the weight, but I don't know the pull of the rope, the tension T. Oh, but wait a minute. I've got that pulley. I know that this guy will cause a torque, and I know what the angular acceleration is through my non-slipping connection. Oh, but then there's the tension on the other side that I don't know. I'm okay, because I can just go over to mass M and say, oh, I'll do a second law for this, find an equation for t prime, put it in here, get t, put it in there, and get m. So if you were thinking about this problem from the very beginning and somebody just said to you, oh, I want to know what the support of the floor is, just remember you may need to go through a series of equations with some other unknowns such that you'll eventually solve for everything and get back to m. Problem 9. I'm throwing a ball across so that it goes through the windows of the car. I know that the velocity of the ball relative to the ground is the velocity of the ball relative to the car plus the velocity of the car relative to the ground. And I know that relative to the car, I want that ball to go straight across. And I know the car, say in the picture that I have, is going to the right. And the resultant of those guys, add those two vectors up, and that's my velocity of the ball relative to the ground. And I know two of the sides, and I can get the angles from trig. A faster way is to just say to yourself, oh, I got this 57 miles per hour, or whatever it is. Oh, I think I can quick look at it. Oh, I don't have that number. But anyway, 57. And I can just simply say, hey, I want the component of this relative to the car to be equal to the car's velocity, so that in the car's reference frame, this thing looks like it's going straight across. And that's a quickie. For problem 10, you know, if I write carefully the FBD for the astronaut relative to an accelerated reference frame, I can answer this. By the way, this spaceship is like a donut with a square cross-section, a big giant donut spinning. And the question we have is, if the people are, spun along with it, I will end up having an effect of gravity. Is it such that the people are pushed against the outside, from the inside of the donut? Or are they pushed toward the inside of this cross-section? Well, if I know that they're standing there in the accelerated reference frame, the net force in the accelerator must be 0. But I know that the centrifugal force, the fictitious force in that accelerated reference frame, is going outwards, and it has to get canceled. Well, which of these sides can produce something that pushes inward? There's only one side that can do that. And that's the side, if you've ever seen that movie, that's the side that the astronauts are walking on. Once you've answered that, you go to B, and you know what will happen then is, if this is the ceiling and you drop it, you know that this light bulb or light fixture is not traveling as fast as the out here, as anything out here, and so it would tend to be behind it if it was falling toward this, if this is the way gravity goes, and vice versa, if this is the ceiling. And therefore, what you know is you've got a deflection to the right or deflection to the left, depending upon your answer for this part. Problem 11. I know that A, it starts at rest, and the value is minus 20, so I know that it's at a minimum, at a trough, at minus 20, And I know it's sinusoidal, so that I actually have my negative peak go through 0 and a positive peak and go through 0 and so forth. And I could even guess that I know what this is. This is going to be just minus 20 in centimeters cosine 5t when you work out what omega is. If you are worried and you say, gee, I don't want to guess it, you can carefully calculate it. You know x, you know v. At t equals 0, then you've got two equations. That has to vanish, and this is minus 20. Those two equations will get you capital A and phi. A is positive, but phi would be 180 degrees in giving you the minus sign that you know you want. In problem 12, well, put all the y on one side and the t on the other. I've got dy over y squared dt, or minus 1 over y equals t plus c, or y equals minus 1 over t plus c. And that's terrific because a small change in c doesn't change y very much. What does that mean? Part B. A strange attractor like the known kind of boomerang, that as we iterated, we found ourselves trapped inside of a region instead of just being sprinkled all over x and y. Well, what about sensitivity to initial conditions? It's okay. If I have two slightly different starting points, when they go and get trapped in the strange attractor, we will not know, and they in general will not be close to, they will stay close together. They might be close together once in a while, but they may be far apart within that strange attractor, and that's what sensitivity to initial conditions would mean here. Finally, in part C, harmonic oscillator, V versus X. If I don't have the units specially, constructed, it might be an ellipse or something like that. But what I know is I start out in time and I go zooming around here and I repeat period 1 and repeats and repeats and repeats in just one period. But in a nonlinear period 2, I would start out, and we'll find that. We'll see some examples of this. I'll come around and I won't repeat there. I'll go around again and then repeat. That would be a period 2. There.